Thank you.
So I'm delighted to have a chance to talk to everybody. This is a fascinating meeting, and I love the degree to which it's, so many different varied participants. I had intended to be there in person, but I have a family member who's sick with COVID, so I'm glad I postponed and not there to possibly spread it to you. I seem to be negative so far. So I want to talk about the idea of using something like the idea floated here for low-cost solar sail missions to actually try to do what I think of as biomap the solar system. Why biomap the solar system? We know that there are some objects that you can see here on my title slide that are hot tickets for potential astrobiological targets. Mars, of course, is one of very long-standing. It's clearly the icy moons like Europa and Enceladus and Titan certainly have significant astrobiology interest about them. But even more recently, we have discovered that potentially Venus may have been a more clement planet very early on in its history. And there were the amazing discoveries that people have made with the New Horizons mission to Pluto kind of has broken open a whole other aspect of astrobiology, not just looking for whole mature biospheres, but looking really at the property of life-bearing from the context of the solar system. So this is actually a paragraph from my abstract, and I don't usually read paragraphs from my abstract as part of a talk, but this one is important because it sets the stage really for what I want to discuss. And this is really thinking of solar systems as belonging to either life-bearing or non-life-bearing categories. And that life-bearing can be full-blown biospheres like that we have on Earth, or it can be perhaps at an earlier stage in various solar systems where they're still in a pre-biological phase. So our solar system is a model for us to develop our ideas that someday in the distant future, maybe not so distant future, we may be able to apply these fundamental ideas to solar systems beyond our own. So life is the product of the solar system in which it's found. This is my contention. This is my assertion. And it's from this stance that I want to discuss what we can potentially do in the relatively near term with low-cost solar sail missions. I love the idea of solar sails. It's not my job to figure out how they work or how they can get us to distant places in our solar system, but it's an intriguing potential avenue to do the kinds of things that I think we need to do on behalf of whole system astrobiology. Oops, it's not advancing. Give me one moment. There. So why do this in the first place? Well, I've argued for quite a number of years that life is a solar system level property. And this means that in any part of our solar system or other solar systems, there are going to be gradations in what I call lifeiness for short. And by lifeiness, I mean the total biotic potential that a given object in the solar system has, or in fact that the solar system has in general. Obviously, we live in a solar system that has produced life. That life has gone on to become quite sophisticated to the point where we actually are conscious beings, bringing us to this point where we're having this meeting. The extent to which lifelike processes and nurturing circumstances extend within our solar system has both an aerial and a temporal dimension. So we are a mature biosphere, essentially in the middle of our sun's lifespan. And so when we look at our own solar system, it's very tempting to think that we only want to consider solar systems and planets that are well into their mature biological phases. But the truth is, it's a very big galaxy, as we know, and we are likely to find solar systems that are both much younger and much older than us, that have potentially life-bearing bodies within them. Some of them have probably already given rise to life. Some of them may have already given rise to life and gone to the point at which that life is no longer existent. So I'm a field scientist. I do lab work in order to give me the chance to go out in the field. But really, when I think of life detection, it's essentially the kind of strategies that we use in a field-based approach to try to study nature in its own context and use the laboratory scheme in order to enrich our understanding of what we find actually in nature. And the approach to how we do this in extreme environments really depends on how much we know about them. So if we have a feature in nature that looks tantalizing, then we do what I call the guess and go approach, which is I might look at a rock outcrop and go, that looks suspiciously like other biomineral deposits I have seen and studied. So I'm going to go there and I'm going to inspect that. But the alternative approach, which is used a lot in ecology, because you are trying to survey very large areas and try to develop a whole picture of the workings and interrelationships of an ecosystem, is to use a grid-based search. And this grid-based search is not based on individual features that you might find tantalizing. It is essentially a mapping exercise. And so it's this idea of a mapping exercise that I think is apropos to our stage of understanding of life and lifelike processes and prebiotic processes and chemical constituents within our own solar system. So one of the things that, of course, is a conundrum that we all face in biology is that life is not a thing. And this is why it is very difficult for anyone to agree on the definition of life, because it really is a set of interacting complex processes. And I think of it as stuff doing something over time. And it's the doing something over time that really is the magic ingredient. So even though a lot of our explorations of the planet so far for lifelike processes have been focused on tantalizing glimpses of potential organic constituents that are used in our kind of life and that we understand quite well in that context, it may be that we are overlooking so many other facets of life. And so in order to be interesting to astrobiology, I contend that you don't have to be dealing with a full-fledged biosphere, because a full-fledged biosphere is part of this ontogenetic origin story and this entire development arc, just as an individual organism has. The biosphere on a planet clearly will have. And so that approach really sort of shifts your thinking about how to go about doing astrobiology in the solar system, in my view. So a survey-style approach, looking at what people are now calling agnostic biosignatures, which means divorced from presuppositions about the particular chemistry that might be involved, but not only just the chemistry, the parts of physics that might be relevant to a particular type of life might be somewhat different from those that are the most relevant to our type of life. And so trying to come up with suites of these agnostic biosignatures is something that has grown in popularity and number of people involved in trying to think our way through how to do that. It is not an easy thing to do. The easiest thing to do on Earth, if you want to look for ancient life, is look for body fossils. This is what our classic paleontology is based upon, and rightly so. But as we go, for example, into the microbial realm, body fossils are either non-existent or they're tiny little blobs that are very hard to argue are organisms. And so we have gone into molecular fossils and geochemical, biochemical fossils. And the same sort of distancing from the obvious is where we're headed in astrobiology again. So besides informing us about our own solar system, one of the things that I think is very salient and of particular interest to a lot of the targets of the Breakthroughs Foundation itself is the idea that biomapping our own solar system may be able to prepare us to be better aware of what we're going to be looking for in other solar systems that we're targeting. So how do we do this? Well, the number one thing that hooked me in to actually talking about this, at this meeting is the idea of cheap bus tickets. And I've known about solar sails since I was an undergraduate, talking to people like Rob Staley and others who were thinking about solar sails, Luke Friedman thinking about solar sails many decades ago, always seemed really fascinating. But now thinking about them as in their current and near-term form as something that's actually implementable with a cadence that can actually do the kinds of survey that I'm interested in doing in our solar system. So the idea of having lots of units, and whatever lots means, I don't know. The way we often do science now, of course, is lots means more than one. You're lucky if you have 2 spacecraft. We have that on Mars. But what I'm talking about is multiple units that can do relatively small jobs. And the strategy relies on the multiplicity of the units and the variety of what you can endow those units to do. So it's more like a breadcrumb distribution. Now, thinking about what I've heard from folks in this meeting and others about solar sails, the most implementable early use of such a propulsion opportunity would be flyby cases. And then there's also the breadcrumb landed use cases that seem to me that they would require significantly more maturity, but could be considered to be on the same developmental pathway. So for the breadcrumb distribution, one of the nicest things about the way a gridded or a swarm approach, people are familiar with that term from robotics, can be implemented is that you don't really need precise targeting. You don't really need steering beyond just getting the landed objects to the destination body. And initially, you can do relatively simple measurements. Obviously, there's all the physical measurements and chemical measurements that can be made. Some of those are amenable to the flyby methodology, and some of them have to have some kind of landed small craft to get to the surface. The eye on the long game aspect that I highlight here really has to do with the fact that from my many decades working in extreme environments on Earth, particularly in the subsurface, what I have learned is that our human-oriented view of what a suitable time frame for discovering whether something is alive or not is highly skewed to the fact that we move quickly, we think quickly, we move about, we're motile. But from the point of view of an extremophile microorganism in an environment where energy is incredibly rare, they have to work exceedingly hard and very cleverly, strategically, in order to survive. Our scale of observation temporarily may have nothing to do with the scale at which they're operating. And so one of the things we have not had yet is really any significant planning for landing small devices that can be watchers, that can be eyes on particular features or on particular bodies. So patience is a virtue. So here's the summary of the challenges that I think are the most significant. The solar system is way too big for just the guess and go approach that we're using now, even though that's well informed for planets that are at least resemble Earth in some way, like Mars. But we need this very large scale astrobiologically meaningful survey. And can we bound the problem of life search and prebiotic indicators by doing this? And can solar sails enable such a survey? In the next two slides, I just want to briefly discuss two potential early use cases, one earlier than another. So very early on in my scientific career, working with Carol Stoker and others, including Vishen Kari and Carl Sagan, we took the tholins, this organic material that they were synthesizing in the Sagan lab, using atmospheres that were representative of different planets. And we took that tholin material and we fed it to microorganisms. We did a bunch of stuff. We eventually squeezed out a paper that was lovely. Carol and I got busy with real life and our other scientific interests. And so it lay there for a long time. And it was only maybe 6 or 7, 8 years ago that I started thinking about that work again, really decades later, thinking about the idea of primitive icy bodies maybe also contributing a free lunch for early life with abiotically produced tholin-like materials. And then I had the opportunity to participate with some of the New Horizons Pluto team, thinking about the tholin-like material that has been seen on Pluto. Never in my wildest dreams, back when I was in my 20s, would I have imagined that there would be tholins on Pluto. So that was an eye-opener. And just this year, of course, the exciting news about 20+ amino acids on Ryugu from the Hayabusa 2 mission has been reported at LPSC last March. And now, of course, people are waiting for the OSIRIS-REx samples to come back. So I think that mapping tholins, which is not that hard to do if you're close enough to a body, is maybe an interesting initial use case to suggest. A much more sophisticated early use case that isn't as early, more like in the NIAC framework, is the idea of looking at energy-based distinguishers between life, dormant life, degraded life, preserved fragments of life, and completely abiotic instruments. This is from the team that you see here at NASA Ames, trying to see whether or not bimodal phase microcalorimetry, which is being used for single cell analyses, could actually be used across a much broader suite of materials. We don't know whether this will work. We were on track to actually do a significant amount of laboratory experimentation on this idea to really do a proof of concept on it when the pandemic hit. And we are only literally just getting back into the lab now and trying to rebuild and fix all the instruments that don't like sitting around for 2.5 years. So we'll see whether that kind of an agnostic signature might actually pan out. Will we be able to distinguish, as this particular paper by Hong et al. Implies that we might be able to do? I don't know. But it's part of this early phase of looking for ways to actually try to map things of biological significance that may not be actual organisms crawling around on something. And so my light sail questions to the light sail community really boil down to this. Can they be maneuverable enough to send a packet or a swarm or impactors to the body of choice or bodies of choice? How cheap and how often can they be launched? And I'm assuming that we have the potential for successive incremental sophistication as we go through these things. And how small and dumb could we make one of these things that we're calling seed pods be to send, tens, thousand, 10,000s, I don't know, in a few kilograms to different bodies to implement this essentially distributed search strategy. So let me end there and thank you for your attention.